The broadcast is now starting. All attendees are in listen-only mode.
Today I'm going to be talking about the pool element. I'll start by introducing it for those of you that may not have used it much. I'll just give a brief overview of how it works, and then I'll talk about how you can, in your existing models that you might be working on for a project, how you might go about incorporating the pool element in a model that currently uses reservoirs. So the pool element is a new element that we've added fairly recently, and it's been around for a little while, but you might have some models out there that have not made use of the pool element. So hopefully this webinar will help you, help guide you on how to efficiently replace the elements that are currently representing ponds or reservoirs or dams with the pool element. And I'll also talk about when you might not want to convert it over. But in a lot of cases, you probably will be better off doing it, and I'll show you why. All right, so what I'll do is I'll show you an example model that what I've done is I've taken some models that I've seen from customers and kind of simplified it a bit. It still includes some of the issues that we sometimes see, and some of the things that can be changed and modified and improved upon to make the model react a little bit better to the information that you're giving it, and also doing the conversion from a reservoir to a pool. But before I go here into this model, I'm just going to start with a brand new model to introduce the pool element to you. Okay, so here's a new model, and let's say that we want to simulate a simple reservoir with an outflow. So I'll start with a stochastic, because this is the fast way to represent time series information without actually having the time series data available. I can use a stochastic to produce random numbers through time to represent what could be like a time series input. So I'll call this inflow, and I'll give it units of cubic meters per day, and then I will just sample from a let's say a log normal distribution, and say it's 10 cubic meters per day with a standard deviation of 1. So the distribution looks like this. I checked fill so you can see it a little bit better. Okay, so we're going to sample random numbers from this distribution, and then I want to sample the random numbers every time step. So I'm going to check here to resample and put a new trigger in here that samples every time the elapsed day changes. So I'll have in this model a 1-day time step, and that's why I want to resample once per day. The next thing I'm going to do is go to the simulation settings and check this out. Perhaps I don't want to run it for quite that long, maybe just 30 days to represent a typical month, let's say. And now I can run the model and look at the results, and we see we have some flow that looks like that. Great. Okay, I'm going back to edit mode, and I'm going to add a reservoir here and give it units of, let's say, cubic meters. And now what I want to do is not only have an inflow here, but I'll call this something like transfer inflow. And let's just say that this is a flow coming from some other source. And then I'm going to add another inflow, and I'll call this runoff inflow. And then I'm also going to autocorrelate this so that it kind of has the appearance of runoff. By autocorrelating, what it does is it samples values that are similar to the previously sampled value on the distribution, so that what you end up with is something that appears to have more of memory as it goes through time. Okay, so now I have these two inflows, and I want to add them to the reservoir. In a real model, what you might end up with is many inflows, and so it might be a good idea to use a sum element to add up all of your inflows and call this total inflows. So I'm just kind of trying to build what you might see in a typical model. And I'll add these two up like that. And then I'm going to add that inflow to the reservoir. So I'll put that over here. And then the next thing I want to do is apply some demands on the reservoir to pull water out of it. When I run the model, if I look at this, we see that it's just growing over time because we have no demands. Okay, so that's fine. The first demand I want to apply is, let's say, a loss rate that's not controlled. You can't control it. It's just dependent on the environment. And I'm going to simplify it by just applying a simple loss rate to request water from it for a loss amount that represents, let's say, evaporation and seepage, let's say. And one way to do that is to enter the equation directly into the withdrawal request here, rate of change. So I could just go in here and say, I'm going to refer to itself, the reservoir times, let's say, 5% per day as a simple loss rate. So this is my constant, 5% per day, and I multiply that by itself, and then rerun the model. And we see this curve because it's dependent on its own value. So you should see a nonlinear curve when you do this. Okay, so that's one way to do it. But if you most likely have multiple withdrawals on your reservoir, right? So it doesn't make sense to hard code them in there. Instead, I'm going to cut that equation out, and I'll put that in a separate equation out here and call this my loss rate. And give this similar units. Cubic meters per day, we'll say, and then put that equation in there. Okay, so we're calculating a loss rate, but this is going to be a feedback on the reservoir, so I would want to add it back in there, but I'm going to have multiple withdrawals from the reservoir. I'll add one more that's just based on a constant demand. So I'll come over here, add some data, and I'll call this mil demand, and then put cubic meters per day again, and say that it's well, let me just take a look at the total inflow so I have an idea of the magnitude. Okay, about 20 cubic meters per day. So I'll say that I have a demand of let's say 18 cubic meters per day here, and that's another demand that I can then apply to the reservoir. So I could come back in here to the rate of change here and say it's the loss rate plus the mil demand. And that's fine for a simple model, but in most cases, like I said, you probably have many requests that you're making on this. And so you probably want to, again, add them up. And so you might put a sum here and say, well, it's the sum of cubic meter per day. It's the sum of our requests. So we might just come in here and say it's the loss rate, like that. Add another one, the mil demand, like that. And then call this the total request. Now I'm being careful with my terminology here, calling it a request and not an outflow. Sometimes what I see is people might come in here and say total outflow, and that kind of connotates here that that this is what you that's what you can get from the reservoir regardless, but it's not the case. The reservoir might drain and be empty, and therefore this would not be the outflow. It's what you're requesting as an outflow. It works fine for something that is a function of the state of the reservoir itself, But for something like this that's a constant, you could easily run out of water, and that would not be the outflow. And so it's important that we remember the terminology. The one I use a lot is request, and we actually use that internally in GoldSim as well. So I recommend using something like that. Anyway, so now we have a total request. We're going to link that to our withdrawal request. Okay, so now you might end up with in your model something similar to this. Obviously with a lot more complexity on how you come up with your total requests that way. And so now when we run the model, we should see that it's not, that it's not rising as quickly as it was before. Okay, so this is all fine. But now what if we have a capacity that we hit, let's say at 20 cubic meters. Okay, so I'm going to add now a new data element and call this pond capacity, and cubic meters. Put that on the upper bound. So I'm going to check the box for the upper bound and add the pond capacity there, like that. Okay, so now we have a pond capacity. When I run the model, now we get this warning that's written to the run log. We should probably check it out. So I say yes, and it shows me here. Hang on a second. Okay. Whoops. There we go. So it shows me here that the reservoir is overflowing, but there's nothing linked to the overflow rate. And so I just need to add another element here that references the overflow. And we do this just to make sure that you're accounting for it. It probably has to go somewhere else in the model. We want to make sure that you do that. Okay, so now it should run fine with no warnings, and now we can plot the reservoir. So you can see that it's hitting the upper bound right there. Okay, so now what happens when we increase our mill demand? Let's see. So we'll say 25. And and by the way, we got another message. I just closed it, but let's look at our run log by going up here to run, view run log, and scroll down, and it says here the reservoir element's outflow has been restricted because it's empty, but there is nothing linked to the withdrawal rate. What this is telling us is that even though we calculate a request here, the actual outflow, which is an output here in the reservoir called withdrawal rate, it is less than what the total request is. And we can check that by adding a time history chart, looking at the total request and comparing that to the reservoir withdrawal rate. So when we do that, we see that the withdrawal rate is down here, the request is up here. And now if we plot the reservoir, you see that there actually is no water in the reservoir at all. Okay, and so essentially what we're doing is pulling everything out of it that comes in. So we went pretty high on that. If I change this to a little bit lesser amount, let's see if we ever get okay, so here we go. Now we have a request that's shown here in red, and then the actual withdrawal is dropping down like this. So we have some shortages going on. Now let's look at the reservoir volume. We can see that it's sometimes it's empty, sometimes it's not. We haven't quite hit the upper bound yet, but I bet if we ran this for a longer period, we would. Okay, so this is perhaps something you might see, but what happens here is you can quickly get more complicated if you have more than one demand. So let's say we have, in addition to our mill demand, let's say we also have to supply water for some sort of truck supply, let's say, or I'll call it truck demand. And let's say that these are both 10 instead of one being 20. I'll just cut them in half, so it's the same total amount, but they're each 10. And so now we can come in here, add the truck demand if we're looking at this in a simple way, and now it would be applied to the reservoir and we'd get the same answer. The problem is there's no way for me to know how much each of these demands get of the request that they're making. What we could do is say, well, if they're equal priority, we'll just assume that they both get, if there's a curtailment, if there's a shortage, then we just cut that in half and provide them. Well, there's an easy way to do that. That is with an allocator. So I can add the allocator here, and I can say same units, cubic meters per day. And then what we can do is add our demands in this list here and allocate them. And so you've probably done this in your existing models or you've seen it. But this way now we can allocate the demands to their individual requests and also use a priority system to do it. So that's really useful for when you're looking at, say, for example, uncontrolled losses like evaporation. You'd want to put that as the first priority. So I'm going to call this one loss, and that's the #1 priority. And then I'm going to call this 2 mil, and then I'm going to call this one 2 trucks. Okay, and now what I can do is just refer to those demands, mil demand, and then, whoops, okay, truck demand, and then this top one is the loss rate. Okay, now what we can do is we can say of the total amount that we have withdrawn from the reservoir, I'm going to move this over here, the total amount of the total withdrawal from the reservoir, now we can allocate it to our individual demands. So that output is here on the output port of the reservoir, and it's called withdrawal rate. That's what I want to link to the allocator. That's what I'm allocating. So then I come back over here to the amount. I say reservoir 1, withdrawal rate. And now what we can do is we can plot the allocated amounts and compare them to each of the demands. So for example, I could say I want to look at each of my demands. I want to look at the mil demand, and I want to look at the truck demand, and then I want to compare each of these demands to the actual allocated amounts. So I'm going to the outputs of the allocator, and I'll click on the mil allocated amount, and then I'm going to truck allocation, like that. And then I'm going to make the colors similar and different line type. Like that. And then run the model. And so now what we see here is we've got lines on top of each other because the demands are exactly the same. So let me make one larger than the other. I'll make this one 12 and this one 8. There we go. So what we're seeing here is that the mil gets everything it asks for, and the truck demand, because it's a lower priority, gets less. And then in the allocator, you have the option to edit your priorities so that they don't have to be a static number like this. And then you can also have equal priorities, and then GoldSim will give you an option of how to share the input or to share the curtailment that way. Okay, so this is a very typical setup that you might see in a model that simulates ponds and reservoirs. Well, let's look at translating this now to a pool element. There are quite a few things that we can now do to simplify the look and feel of this model with the pool element. So now I'm going to add the pool here. And somebody asked, is it possible to use a stage storage curve in the reservoir element to analyze the response of filling the reservoir? And the answer is not inside the reservoir, but yes, indeed, a lot of people use a lookup table to reference the volume that's calculated of the pond, and gather from that the elevation or the water surface area, and make decisions based on that. So yeah, we can, and in fact, the application I'm going to show you next will use that functionality. Okay, so the pool element. So here's the pool element. It has a by default the name pool, and we did this on purpose because we didn't want to conflict with the name reservoir. The pool element is essentially what you see on this page with some things combined, actually. So the pool element is like having a reservoir with the summation of inflows embedded in it, and also the allocator embedded in it. It's like having all three of these items. In fact, I'm gonna draw a box around that. So the pool element is like combining all of these things right here. In fact, you could also simplify it a bit more. In fact, I'm not telling you exactly right here. I should bring this down a little bit more. So it's actually including this guy too. So it'd be like including that. And the nice thing about the pool is by using the pool, because you've combined all of these elements, you can develop a model that looks and feels a lot more like a schematic diagram of your flow system, which I'll show you some examples later that demonstrate that. But anyway, what we're going to do is combine all of this stuff into this one element. Okay, so I'm going to save this model now and then start fresh with where we left off with a new model. So let me just call this webinar reservoir model. Okay, now what I'll do is save as, and I'll call this webinar pool model. Okay, all right, so now I'm just going to replace all of this stuff. And to do that, the way I suggest you do that is you keep the reservoir there and you just add a pool, and you just, I guess, kind of go back and forth and look at how your reservoir is set up and just kind of replicate that over into the pool before you delete the reservoir. Because like I said, in a big project model, you've got a lot of complexity here, and it's not a good idea to just wipe it out. Or you could put two models side by side, right? I could put the old version over here, the new over here, and copy paste and so forth. That might be the easiest way. But anyway, so I'm going to start with the sums here. I want to add the runoff inflow and the transfer inflow to my pool element. Okay, but before we do anything, we need to make sure that we get the display units correct. I'm also just going to call this pool, not pool one. And then I'm going to come down here to the quantity units. That's the amount that is being accumulated in this pool. And so that's cubic meters. It's in terms of volume. Therefore, the flow type units here have to be consistent with a volume. So it has to be a volumetric flow rate. So I'll say cubic meters per day. Okay, so now that we got the units set up, we can go over here to the inflows. Oh, and by the way, I also have a capacity that we'll add here as well. But let's start with the inflows. So in the inflows, I have two. One way to do this, if you have equations that need to be put in here, or a lot of references that you know about that you want to just type in, then I would suggest you just click add and then escape key multiple times. You could do that. Or you could just hit add and browse in your model to the element that you want to link to, like that. But by hitting add and then escape, then it allows you to come in here and copy and paste. Let's say if you're referencing an old model and you just want to copy and paste an equation, then you can put that in here as well, or of course type it in. Either way will work just fine. Okay, so and it actually works very similar to the way that the sum works. But we can also move these up and down if you want to. If you have high priority ones that you want to look at first or something, then you can do that. But just keep in mind it works exactly like the sum element does. It's just going to add all these up. What's nice about this pool element, though, is if you go to the output port of the pool, you'll see there are a lot of different outputs available. One of those is the total inflow. So even though you've embedded all of the inflows into this pool, you can still look at the total of all those inflows. Now, it doesn't allow you to reference the individual inflows, only the total. So keep that in mind. Okay, so we've taken care of the total inflows, and we can probably just go ahead and delete that. All right, so the next thing we want to do, and obviously the model's broken now because this reservoir doesn't know what total inflows is anymore, but we don't care about that. The next thing we want to do is add the capacity. So I'll go in here and check upper bound and put pond capacity there. And then we want to go look at the allocator and replicate everything we're doing here. Okay, so the one nice thing is we don't have to worry about referencing its own withdrawal rate anymore. All we need to do is put in all of our demands and their priorities and give them labels, just like we did with the allocator. So I'm going to do that by opening up the pool and going to the Outflows tab. And then we're going to have 3 outflows, just like the allocator has. And then I'm going to give them each labels. Evaporation. Actually, we called this one losses, didn't we? Losses. This one was, I think, mil demand. Actually, I'm going to call this 2 mil. 2 mil. And then this one is, because this is, we're actually labeling what the delivery is of this supply, and not necessarily the demand here. We will define them, the request, as a demand, but the output here is the delivery. Okay, so now I could just refer to the loss rate calculation that I have. That's this expression right here called loss rate. That's one way to do it. Or you could put the equation itself in there. The only reason you would really want this loss rate out here is possibly for just to show it visually, or if you thought that this request would be different than the delivery amount, then you might want it to provide it as an output to view the results of it. But in my case, it's always going to be the same as the outflow because it's a function of its own volume. I'm therefore going to copy the equation, and I'm going back into the pool, and I'm just going to get rid of the loss rate altogether and put the equation in, bypass all of that. But it's referring to the old reservoir. We want to definitely change that to pool because we're referring to this thing itself, the pool times that loss rate. Now, for an evaporation, you might be referring to the ponded water surface area, obviously, times some sort of a length per day or length per time multiplier, and that's fine. But you could put that whole equation in there. And the nice thing about this is we've simplified the model. We don't need that element anymore at all because we've got that equation right there. The other ones, they're demands that are defined externally, so we have to enter those in by referencing mill demand and truck demand. Okay, so now we can totally get rid of this allocator, and we can also get rid of the total request. And essentially now everything is all assembled just the way we had it before, and now I can get rid of the reservoir, and now we're left with this. Of course, our overflow is not quite right, so I need to re-reference that. The pool dot, and here are all the outputs of the pool element. The one we're looking for is overflow. Keep in mind that it's now called overflow and not overflow rate. And so if you're referencing those kinds of outputs throughout your model, you will have to change that to be overflow. Okay, let me just hit my F9 key to make sure that everything's connected, and it is. You can also go up here to model, update expressions. That's F9 key. That just makes sure that everything is all linked up, and it is. And now we can go back to our chart and say, I want to look at the demand versus the delivery. And we no longer have an allocator, so we need to look at reconnecting that, and that's the pool output. And then in the pool element, there's a folder called outflows. So these are all of the outflow requests that we put in, and it then turns around and gives us the actual delivered amount for each of those requests, and that's what you see here. So I'm going to click on that one, 2 mil, pool outflows to trucks. Now we run the model, and I still have a warning. I'm going to look at it. It says the results element contains one or more incomplete results items. Oh, that's this one over here. So this one, I need to go back to edit mode. What am I missing here? Total request. Okay, so we can still get the total request. That's right here. And the reservoir withdrawal, that's the total withdrawal. So we'll go pool and total, oops, no, not total request, total outflow. And then the the labels are still the same as they were before. So you may want to change those. And over here, we'd probably call this total delivery. And we need to be careful with how we say delivery. That includes the losses. So if we probably don't want to say delivery, we probably should say total outflow. Total delivery would be the sum of these two deliveries, and not including the evaporation and seepage losses. Okay, so we run the model, and we see a result that's exactly the same as what we had before. So this is a good way to convert your reservoir model into a pool. All right, so let's open these models side by side. And the other one, pool model. The other one is the reservoir model. Okay. So there's the comparison that we have. So you can see it's quite a bit simplified there compared to what we had before. Okay, so that's a good way to switch your model over to use the pool element. Now what I'm going to do is show you more of a realistic model, something that you might see for in a real project. So I'm going to go ahead and close these, and like I said, I'll make these available for downloading after the presentation. So here is a model that I've created this, but it really is based on in fact, just recently some models that I've seen from some users, and so it's pretty realistic for what you might see in yours. What we have here are 3 ponds, and this first pond, the way that it works is, and I need to move some arrows so you can see everything here. Okay, the way it works is that it needs to deliver water to pond 2, and it might overflow. If it does, it sends it to pond 3. Same thing over here. If pond 2 overflows, it sends it to pond 3. So pond 3 is kind of like the catch-all for any overflows that occur. However, there's a little bit of a complication, and that is that pond 1 needs to look at pond 2. It needs to check it out to see if it needs to send water over there. It only sends water over there if it's not full, essentially. In the most simplistic way to express it, that's kind of what it's doing. It says if pond 2 isn't all the way up, filled up, I'm going to send some more water over there. If it's full, then I'm not going to send any water over there. That's the way that it's working. Okay, what I'm going to do is just run the model, and we're just going to look at the results, and we're going to ignore the warnings here for now, and we're just going to look at this result. What this is, and I probably should relabel I need to relabel this y-axis here because it just says 1. These are referring 1, 2, 3 refers to pond 1, pond 1, 2, and 3. So I probably should have said ponds there, but anyway, I'm just going to change the y-axis here so that makes more sense. I'll call this water levels. Okay, so the water level in each of these 3 ponds looks like this. This is a deceiving plot right now, the way it is. The reason for this is because we have many inserted time steps in this model. And you can always determine if you have inserted time steps if you change to the table view, but only under the condition that you're looking at high resolution results. So right now, you see it looks like we have 1-day time steps by looking at the table. But what we need to do is we need to turn on our high resolution results for time histories so that we can visualize when we're inserting time steps. So I'm going to do that now. Go back to edit mode, go up here to the simulation settings, and then go to the advanced and check this box that says include unscheduled events, high resolution results for scalar time histories. If you have a vector connected to a time history, you can't see it. If you're running Monte Carlo, you're not going to. You need to run just a single realization for scalar outputs, and you'll see the high resolution results. This is important. It's a good way to debug your model and find places that are possibly not working the way you expected them to. So I'm going to run the model and look at this history, and now we see something different. It looks a bit different. We see these oscillations, is what I like to call them. If I zoom in here to this little spot, and I can keep zooming in, you see that things are happening, they're kind of oscillating back and forth. So here's something that says, December 11th at 14, and then same day, 3 hours later. So every 3 hours. But here's something that looks like it's occurring much faster than that. So I'll look at the table view, and you can go in here and see how close together these time steps are. They're pretty close together, actually. Some of them less than an hour. So if you come down in here, you'll see that they're getting pretty close together here. Perhaps not something that you expected. In fact, if you look at some of the flows that are getting passed around, let me see what we see. Let me see what we find here. Okay, so here's something that you may not have seen. In fact, let me do a time history chart, because that's the only way to look at high resolution results is with an actual time history chart. So I'm going to add from, let's see, water supplies to pond 2. I'll put that in here, run the model, and we see this value. We see these, these spikes that might be fairly high, something we may not have expected. Also, some of the overflows that we have might be a lot higher than what we expected. It might even exceed the capacity of what those flows can pass. In this model, we were dealing with pretty low flows, and this is a very, very large number, something that's not even realistic. So how are these things happening? Well, what I would say, if you run into this kind of issue here, what I would suggest that you do is, one of the first things to look for, obviously, is what I just showed you, is the high resolution results. But then to come over here into your browser, select Show Element Subitems, and then go into your local properties and look at the time step length result. So this is a run property in GoldSim that tells you how long the time step was since the last update. And if you recall, we had some inserted steps that were inserting steps, within an hour, and so that means that the time step length value would be, maybe an hour or less or something, some short time that's less than a day. And you can see here that there's the symbols next to these are gray, but the one next to time step length is blue. That indicates that it's being used in the model. So what we can do is click on effects and find out where it's being used, and it shows us it being used in all of these places. And so what we'd want to do is double click on them and look at the equation and say, okay, does it make sense? Let's say that this is a value of, let's say, 15 minutes. It's a very short time frame, because that's the time since we last updated in a certain time step. If that's a very small number, is this going to provide us a number that is reasonable? So you'd want to go through your model and think about that. If this was intended, which is often the case, to be just a constant, 1 day, that is not what's happening in this model, then we'd want to create a global variable called something different than this, let's say dt or something like that. Then we'd want to refer to that when we're using this kind of equation. But there are times when I might say this whole approach should be different than what's going on here. But we don't want to get too far down that road yet. Let's first talk about how this model might be simplified by adding the pool element. Okay, so if you go into each of these ponds, you'll see there's all this stuff going on. They all look fairly similar. They have some multiple runoff or multiple inflows coming in. We've got runoff that are coming from multiple places, and then other flows that are coming in. Some are defined locally in here. Some are coming from outside, and you know they're coming from outside because of this dot that's on the input port, indicating that an output is being referenced from outside of this container. And then we add those up and we put those into this reservoir. Now it's called pool, but it's really just a reservoir element. This is your typical reservoir element here. And then we use this allocator. In fact, this model is using two allocators, one for evaporation and then one for water supplies, because the way that it's working here is it says no water supply can be delivered if the water level drops below some value. In this case, a dead storage volume here, which is defined there. If your water level ever drops below that, then you have to curtail your water supply. We obviously don't do that for the evaporation, and that's why we have two of these going on here. Okay, so each of these ponds look similar here. So what I did is I went ahead before this presentation and modified this model to use pool elements. So let me go ahead and just save that, and then I'm going into the next version. Here's the same model, but now with pool elements. And so you can see that it's reduced down quite a bit, simplified quite a bit. Now instead of using two allocators here, I removed both of them, and instead in the equation for the outflows, I put in here an extra min function for what we had before, in which we said we need to make sure that we don't allow it to drop below the dead storage. Again, I would do this differently than what we have right here, but essentially I just replicated the allocator that we had calculation and put that in here. So both the 2 pond 2 and the 2 truck fill outputs, they are being controlled by this dead storage volume, all inside this one request. So you can see that it's getting a little bit cramped in here. It might be a better idea to put this in an expression that's just sitting outside, but you don't have to. And sometimes I prefer to put the equation here just because you can plot its output. You can look at the equation just the same, and then it doesn't require that you have all these additional elements sitting around it. And it also forces the user, if they ever need to look at the delivery amount, they always go to the outflows of the pool to reference it. They would never mistakenly go to the request that's outside here. They would always go there to find the delivery from this pool. So I think it provides a bit safer environment for when you're working with a team on a model to reference outflows. Okay, so when we run this model, and I'm just looking at the advanced settings, we are not looking at high resolution results. If I run this model and look at the results, you'll see something that doesn't look like that. It looks sort of similar. You can see it's a bit more simplified here, but one thing we'll see now is when I turn on the high resolution results, then you'll see there's oscillations again. So we're still getting some oscillations, but we're getting pretty much the same result as we did before. And then the next step that I did, if I go in here and go to the next one, in the next iteration, what I did is I removed the time step length reference that was up here, time step length. So now you see it's not being referenced at all. And I created this global variable called dt, and I defined it as a constant, 1 day. And now, if I right click and select effects, I go to the equations that's using it. Instead of using time step length, the run property, I just refer to the global dt, and the equation is exactly the same, but now it's referring to a constant and no longer referring to something that could be possibly very small and also dynamic and not producing the results that you're expecting. So this is an important change if you have equations that are using time step length. But again, I would recommend looking at changing how the approach to some of those calculations, which I'll talk about just in a second here. So when I run this model, you'll see that this green line looks like it's running along nice and flat there. If I go to the settings here, advanced, you can see I'm looking at unscheduled updates. So we are looking at unscheduled updates. We don't have the oscillations going on anymore. Those oscillations were indeed caused by the reference to the time step length, because we were producing these very large flows when we shouldn't have been. That was not real, and it was an artifact of referring to that time step length. But you can see we still have some of this going on, some of this thing, and this really is because of the way that we're calculating the curtailment of our water supplies at the dead pool level, and that's over here in pond 1, this thing I was describing earlier, where we have this dead storage volume, and we don't want our pool volume to drop below that amount. Move this up a little bit here. Okay, so what I would suggest you do in a case like this, I see a lot of models where people do this kind of thing. What I would suggest you do instead of this is use a status element. And in our help center, which, let me just open this up as soon as it comes up. Okay, so in our help center, I would suggest going there to our model library, and so you go to our model library, and then we have examples here where we're using the status. I think if you just type in status, reservoir discharge controlled by status, that's the one that you want to look at there. This is the approach that I would highly recommend that you use instead of what's currently going on. What this allows you to do is provide some delay in the response and avoid any kind of artificial high flows or oscillations that may not actually occur. So that would be useful. And then the other thing that is going on here is if you go over to pond 2, one other thing that's happening here is they're saying, well, I want to ask for water to come in here by calculating a discrepancy between the total capacity volume and its current amount, and then just divide that by 1 day. So what they're doing here is they're saying, let's say I'm 5 meters below the top, and I need to figure out what volume that is between those points, and then go ask for that volume to come in here over the course of 1 day. What I would say I would say also use a status element here, and I would say try to maintain some sort of target level, and if that's the top, that's fine, but allow it to draw down just a little, because that's how it's really going to happen in the real world before you ask it to turn back on. Now, if you have very large time steps and relatively smaller storage volumes, then you may have to resort to this type of logic, and that's fine. But in a lot of cases, you don't. In a lot of cases, you would actually operate it the way, or you would model it the way it's actually being operated, which is using a target level. So it all depends on the coarseness of your model. Some people are doing simulations that have 1 month time steps, and this kind of approach is fine for that, but just be aware that you might get oscillations with this kind of a thing here, especially if you've got feedback between your reservoirs like this, which is the case for us. Okay, so those are some of the additional changes I would make to this model that I have not done yet. That being using the status element approach. So that's something I would add in addition to this, what we have in this model right now. Okay, I want to show you one more thing, and that is a comparison of how you might build models that involve pool elements. So I'm going to close this down, and I'm going to open another model. This model you can get from our model library as well. But I've created some that are they're all built in a little bit different way. It's the exact same model, just built in a different way. So I'm going to start with this one. Okay, so here's a model, and in fact, I'm going to put some things side by side here. But this is a very simple model where we have a river, and then we divert water from this river. It goes into this pond, and then overflows go into this pond up here, and we drain water back into it. It's either that or we feed water to it and the overflows come back. It's something like that. But essentially, they're just kind of cycled around on this one. And then this pond feeds pond 2, which then delivers water to these 2 delivery points, and return flows. Some of the return flows come back to pond 1. So you can see a lot of things going back and forth and around. And then you've got these green lines. Now I colored these lines differently to represent different kinds of influences. This is sometimes important when you're trying to understand the overall system. You might have what are called feedback influences, and that's this green line, as opposed to an influence that represents the water that's moving, or the thing that you're modeling, the material that's moving. I like to color code these so that it's not confusing what's going where. We don't actually send any water from pond 2 to pond 1. All we're doing is we're referencing an output from pond 2 over here so that we know how much water to send that way, if that makes sense. You can also double click on the line to see what it's doing, to see what it's sending. So for example, at this diversion, we're saying that I'm referring to a priority value at the diversion point that's based on the priority of this demand down here. So the priority for water at this point is being used at the diversion. We don't want to confuse this influence line as a water flow, so that's why I've color coded it. And I did that just by right clicking on the line and going here to color and changing it manually. By default, the lines all have certain colors, and you can look at those defaults by right clicking in the graphics pane, going to the properties, and looking at these defaults here. I've changed the defaults though. It's actually black when you first open GoldSim for the value lines. I changed them to blue. Okay, so this is one way to do it, and in each of these containers, it's got everything about the pond. Now, again, this is using reservoirs, so it's the old way, and we could simplify it quite a bit by adding those pool elements. Let me show you another way to set up the same exact model. Here's another way, also using reservoir elements. I'm going to move this one over. Move this one over to the side. There we go. And move this one over. Okay, so space is a little bit cramped here, but anyway, this model over here on the right is exactly the same thing. All I've done is remove the containers, and I'm only including the flow related expressions in this container. So if I browse up one level, you'll see what I've done is I've moved a lot of the input data. So if you look at, say, for example, a single pond over here, you see it has some input data: pond capacity, initial volume, some evaporation stuff in there, etc. So another way to organize your model is, instead of creating a localized container that represents everything about that pond, you could put your input data elsewhere and feed that input data into, let's say a flow network, so that you can isolate only the parts that have to do with the objects that are sending flow one way or another. And then there's another part, and that is the feedback, or the state of the system, that's going back and forth, like it's causing these green lines to go back and forth, um, that could also be taken out. But essentially, you can see it's the same thing. Now we can kind of draw this model to represent all of the flow items in here. Um, and so you can see how um, everything is blue lines. We have nothing talking back and forth in this level. There's the volume in pond 1 is actually a function of what's in what's in pond 2, but that's being taken care of at this upper level with this line right here. So this influence, if I follow that, you'll see that I have a pond volume vector. What that does is it says in the entire model, what are all the pond volumes, and then I can put that into a vector and calculate the pool areas for all the ponds and the percent full for all the ponds, because that's what I'm using to trigger controls for flows and so forth. So I'm essentially, what I'm doing here is I'm passing some of the state variables like volume and water level and so forth. I'm passing those over into the inputs, doing some things with it, and then driving what those flows would be. So that's one way to do it. Another way that I think is even simpler is, oh, let's see, I should probably just reopen, then I can go back to the same place. Another way to do it is, let's see, I think it's this one. Yeah. Another way to do it is using pools, obviously. With the pools, it simplifies it greatly. We don't have the allocator sitting there next to it everywhere. So this is essentially the same thing that you saw before, but now I've converted it to pool elements. You can see that we've pretty much fit the system in this space that we have shown over here. It's the same exact system. But because they're pool elements, now I can greatly simplify what we're showing, and I don't need to include all of those allocator elements and some elements, because those are included in the definition of the pool, in the inflows tab and the outflows tab. And I've essentially encapsulated all of that, all of those expressions inside the pool, so that now it makes it very easy to represent this system with just the flow links. I've not hidden any other influence lines in this model. These are all the influence lines within this container. But I went a step further in this approach, and if I zoom up, what you'll see here is I've created what I'm calling flow drivers, and this is essentially where I pass the state of some of the variables, like let's say, for example, all the pond volumes. I pass those in here, and then I calculate things like how much water needs to pass from one to the other and so forth. And then I feed those back into the flow network calculation, all in an effort to organize the model in such a way that we show a schematic. So these two approaches, the one on the left and the one on the right, are both correct. It's just a different way to represent the system. And one thing you just need to be careful of when you're building a model with containers, which there's no problem doing it this way, is that you just need to probably differentiate between the feedback lines and the water flow or material flow lines to better represent a schematic of the flow system, if that's what you're after. If you really want to show a schematic of a diagram of where the water's moving, then I suggest you do it that way. But by converting your reservoirs to pool elements, it does lend itself better to representing just the flow network in a container like this one on the right. So I'm really excited about the pool element and what it can do for your models, and I think it will make a big difference. I've already noticed it making a huge difference in a lot of the models I've worked on, really simplifying a lot of things, but it's a very robust element and really helps with the visualization, I think. So one limitation of it that it doesn't have, that the reservoir does, is the ability to have a non-scalar. So a reservoir element you can make make it as a vector or a matrix, to represent many storage items, but the pool can only be a scalar. So that's one limitation there you want to be aware of if you're looking at doing conversions. All right, so that concludes the presentation. If you have any questions, I'd be happy to answer at this time. So I'll just hang around here a bit and answer any questions if you have any. Thank you for joining. I hope this was useful. And again, I will be posting this on our website, and I hope you can join us next month for a presentation. And I should probably point you to it. Let me go to our website. Look at the schedule for this year. The next one is going to be a guest speaker, Nicholas Brink with Stantec. He's going to talk about modeling consolidation of slurries using GoldSim. And we're pretty excited about this one. It's always nice to have a fresh voice on our webinars. So I highly recommend that you watch for the email announcement about this one. If you're not on our webinar email list, please let us know and we can add you to the list. But thanks for joining, and we'll see you next month.